will not proceed with opening remarks because we would like to do things differently and immediately enter the core of the subject and be very pragmatic during this webinar. So if I may, I will first start with Stefano. If you can please let us know about how to compare green hydrogen and green chemicals for European imports from Africa, thereby highlighting the opportunity each offers. Please, Stefano.
Good morning, everybody, first of all. And let me thank again MedGem Network also for, let's say, the possibility for being together in this webinar. I hope you can see my screen.
Yes, Stefano, but we see the presentation with the notes.
Okay, sorry for this, 1 second. I'm sending again. Now it should be better.
Perfect.
Okay, following up what we introduced the last time for what it was Just Green Africa project, just few words to remind the attendees of what is Just Green Africa. Just Green Africa is a Horizon Europe project financed by Clean Hydrogen Partnership and the European Union, whose goal is to promote cooperation between Europe and Africa in the field of green hydrogen transition. The idea is indeed to reconcile somehow the needs from Europe from the hydrogen import point of view, recently described in the Repower EU plan, and from the other side, exploit the, let's say, great hydrogen potential that Africa has, and let's say, trying to coordinate this potential offering from Africa and this potential need from Europe. As I mentioned, therefore, Europe is, according to the Repower EU plan, going to need up to 10 megatons of green hydrogen per year for its own business. As you understand, this is a quite huge amount of hydrogen that somehow has to be, transferred and transported to Europe. And this transport is actually the main challenge, because at the end of the day, as you know, hydrogen is a gas, is a very light gas, and therefore transporting hydrogen for long distances and in large amount could be not so simple, okay? You have to consider indeed that the maximum density that hydrogen can reach, even once it is liquefied, and we have to remember that hydrogen can become liquid only at around 20 Kelvin, the maximum density that hydrogen can reach is around 70 kilogram per cubic meter. So something very, very low, particularly if you compare it with whatever else fuel, liquid fuel like gasoline, diesel, or let's say components like this. So one among the possibility to transport hydrogen, there is also obviously the possibility to transport hydrogen not in a pure form, but via the so-called hydrogen carriers. So chemical components, including hydrogen, that are easier to be transported, like, for example, ammonia or methane, methanol, let's say, what are also called e-fuels, as well as one way could be even to, instead of transporting hydrogen, to use hydrogen captively in Africa and somehow export, instead of hydrogen or hydrogen carriers, products that, are realized and manufactured thanks to the use of green hydrogen, but that are easier to be transported, for example, because the value chain and the logistic value chain for transporting them is already in place. So this presentation has the goal to try to understand what is better to export from Africa to Europe, if it's better to export hydrogen carriers, or green hydrogen-based products. This analysis will be performed This analysis will be performed, let's say, from a technical and economic point of view. Most of all, I would like to mention first that we have to consider that if we look at the currently announced projects, many of these projects are actually targeting the possibility to use hydrogen at local level, maybe in the local production, but many others are looking at full export of hydrogen. This analysis, for example, comes from deliverable 1.1 of Just Green Africa that you can find directly on our project website or on Cordis. So the goal of today is to try to find a rationale and answer to a main question that comes from also from this assessment of the announced project. So is it better to produce hydrogen and use it locally from also, let's say, from an environmental but also economic point of view? Or is it better to produce hydrogen and transfer this hydrogen for Europe, for example, to produce some products in Europe? And we are going to do so, and we are trying to answer to this key question, mostly looking at what? Mostly looking at two categories of products. A category of product that we call combustion products, meaning products that use hydrogen in the let's say, use hydrogen as alternative fuel for the combustion processes that are implied in the manufacturing process, and see what we can call synthesis products, meaning products where hydrogen is used as basis in the synthesis of the carrier. So we are talking mostly of chemical components, of course. I kindly ask to my colleagues if, while I'm presenting, if you can accept people connecting, because unfortunately I cannot. Thank you very much.
Yes, I do.
Perfect. So this is the key question, and these are the two categories. The whole analysis that I'm going to present you is part of the Just Green Africa project activity, and start from what? From, first of all, an assessment of the cost of production of green hydrogen, so hydrogen produced by electrolysis, in different areas of our three reference countries that are Morocco, Kenya, and South Africa. In the framework of Just Green Africa, indeed, we identified what we call hydrogen hubs, so places where we can study the production of hydrogen and the potential use at local level of hydrogen, mostly because of what? Because of the good presence of renewables in such places, but also because of the presence of relevant industrial sites in the area. So the full analysis that I'm presenting today starts from what? From the evaluation of the cost of production in these hubs. This is an analysis that we performed, calculating per each hub what is called the levelized cost of hydrogen. How the levelized cost of hydrogen is calculated? It is calculated mostly looking at the annual production of hydrogen, starting from the annual production of the local renewable power plants, looking at the full capex and opex of the green hydrogen production plant, so of the electrolysis plant, and let's say assessing the amount of hydrogen that can be produced along the project lifetime, try to understand how much is the cost of 1 kilogram of hydrogen in the overall lifetime of the electrolyzer. So we start from this value that, as you could see, are very let's say, attractive value, because we are talking about the cost of green hydrogen that and of pure green hydrogen. I mean hydrogen that is produced, for example, via PEM electrolyzer, that is very competitive, because we're talking about costs around €5 per kilogram, with even areas like the Olkaria geothermal power plant where we can get up to $2.5 per kilogram. So we start from these values, and per each hydrogen hub, per each hotspot that you can see, so per each area, considering the industries that are present in each of these district areas, in each of these industrial district area, we are going, starting from the costs of hydrogen that I showed earlier, we are going to calculate the cost of production of different products. So in generally speaking, we are mostly considering, as I said, combustion products like concrete, steel produced via DRI, and among the so-called synthesis products, we are looking at mostly ammonia, formaldehyde, urea, methanol, and gasoline. Why these products? Because these products are, let's say, you considered, let's say, for what it concerns combustion products, we target still concrete that are so-called hard-to-abate industries, so industrial sectors where the use of hydrogen is deeply investigated. And for what it concerns urea, methanol, formaldehyde, ammonia, and gasoline, we are talking about chemical components that are already currently produced in Africa and, let's say, already exported from Africa to Europe. Obviously, we have also to study how to transport these products or the pure hydrogen from the hotspot up to Europe. How we did it? We did it considering two destinations. One is Rotterdam and one is Genova. And we did it considering as mean of transport, ships, trucks, and natural gas pipelines in the case of evaluation, obviously, of the potential transport of pure hydrogen. That, as you remember, we already discussed about this during the previous webinar, thanks to the support of Artelis colleagues. So, particularly for, let's say, products and carriers, we always consider, for example, the possibility to use truck up to the closest port, and then the ship to transport this, let's say, product or carrier from the hotspot up to or Rotterdam or Genova. In order to evaluate, let's say, also the environmental benefit and the difference in cost with traditionally, let's say, traditional production processes, we took as reference the possibility of producing combustion products instead of via natural gas, via using gray hydrogen, so hydrogen that is produced from natural gas steam reforming. What we did at the end, per each product, so concrete, steel, and steel DRI, we first of all calculated the cost of the product as it is, so without using natural gas, and the cost of carbon tax, let's say, per ton of product, considering a cost of carbon tax around $70 per ton of CO2. In this way, we calculated more or less the cost of the gray product. What we considering with gray product, we consider the product using natural gas as combustion fuel. Then we made the first estimation, and we considered instead of using natural gas to use gray hydrogen. Okay, using gray hydrogen, we kept more or less let's say we reduced, of course, the amount of CO2, because the amount of CO2 is lower, because gray hydrogen has a CO2 footprint, but just in its production, because during the combustion, obviously, it has not. And we calculated the, let's say, percentage of cost of gray hydrogen on the cost of good, because at the end, the carbon tax on the product will be lower, but the carbon tax will be only on the gray hydrogen. And we saw that using gray hydrogen, at the end of the day, we will increase around 15 up to 30% the cost of the overall of all the goods, more or less. Then we did the same exercise, starting from what? From the cost of levelized cost of hydrogen in the different hotspots, in the different use cases. And what we saw is that in order to fully decarbonize the production of these combustion products, actually the cost of the products becomes quite relevant. They can even double, okay, even double or triple, okay, with the cost of green hydrogen, that becomes quite significant on the overall cost of the product itself. And also we compared how much is the difference between the cost of green hydrogen and gray hydrogen in the difference area, highlighting that, again, the difference in terms of cost of using green instead of gray hydrogen is quite significant. Then what we did an analysis mostly in terms of looking at transportation and production cost, and comparing the different overall cost that is a sum of production cost and transport cost, with transport cost calculated for both Rotterdam and Genova, as you could see, with the reference values. So what you can see is that for a product like steel that requires a very high temperature in its production process, the fact that we use green hydrogen double or triple, as we said, the traditional reference cost, the so-called gray product cost. It is a little bit less intensive if we look at concrete, where we are not getting up to the double, and where, let's say, and even less for steel DRI, so where the hydrogen is used as reduction gas. So for combustion processes and products, let's say, we can state that the possibility to use green hydrogen in the manufacturing of the products, except for steel, obviously has an increase in terms of cost of production, but if we look at the higher value from the environmental point of view, maybe this could be something that can be remunerated, and therefore, you know, even if I pay more to produce my products, I can sell it at a higher price, for example. Let's do the same, let's say the same exercise for synthesis products. Here we divided the synthesis products in synthesis products coming from nitrogen and hydrogen and CO2 and hydrogen. So from nitrogen and hydrogen, the products were ammonia and urea. And in this case, we further than considering the different, as we did earlier, so the different cost of the gray product, the different cost of the product using gray hydrogen instead of natural gas, and the different cost of let's say the products in the different hubs looking at green hydrogen instead of gray hydrogen, it is important to say that for the synthesis of these products, we have to consider also an emission factor and a cost factor that is related to the electricity cost and electricity grid emission factor at local level for the production of nitrogen via an air separation unit. So as you can see, once we look at the different costs in the synthesis of ammonia and urea, the location has an impact for two reasons, not only for the different levelized cost of hydrogen if we look at green hydrogen production, but also of the different local electricity cost. What we can see in this analysis is that if we look at synthesis products like ammonia and urea, the possibility to use green hydrogen is quite, let's say, cost demanding. So we are again doubling, more than doubling the cost of production, mostly because, you know, as I said, we have a large amount of hydrogen needed for the synthesis of these products. Obviously, if I'm able to rely on lower cost of electricity, both from the renewables and from the or from the grid, this have a double impact because this lower cost of electricity has an impact both on the hydrogen production and from the nitrogen production point of view. We did similar exercises, I mentioned, also for, let's say, the CO2 and hydrogen synthesis products. Here, in this case, you know, we considered formaldehyde, methanol, and gasoline. Formaldehyde, just for, you know, it's coming from a partial methanol oxidation, so it's a sort of first post-processing of the methanol, and the same is for gasoline, that is, again, a further post-processing of the methanol. What we can see is that, as it happened more or less for ammonia and urea, in the case of methanol, in areas where the cost of electricity is high, the cost of the synthesis of the methanol, because here we have also to consider some electricity needed, some energy needed for the synthesis of the reactor. Obviously, if the cost of electricity is higher, like in Dakla, the production cost becomes more than the double. While in area where the electricity cost is lower, or the levelized cost of hydrogen is lower, we are able to get not so bad values in terms of cost of production. The the more hydrogen I need in my process, and of course, the more the impact of the levelized cost of hydrogen and the impact of green hydrogen cost is becoming present, okay? Because, for example, if I'm not able to get very low cost of hydrogen, for example, in case of gasoline and formaldehyde, I again double the cost of manufacturing. Nevertheless, what is relevant to say is that, okay, it's true that the production cost, if compared with gray products or products realized via gray hydrogen, are much higher than the are much lower than the production cost via green hydrogen. But at the same time, what is very relevant to say is that, as you can see in these two graphs for Morocco and South Africa, the cost of transport of products is more or less negligible if we look and if we compare to the cost of transport of hydrogen. So what we are stating is that generally speaking, the cost of transport of all the proposed goods, but particularly for what it concerns combustion liquid fuels like gasoline or methanol, or in any case, let's say, products that are liquid, the cost of transport becomes negligible, even if maybe the cost of production is higher than the gray one, okay? And, therefore, producing locally products from green hydrogen is something that is, at the end of the day, more valuable and than transporting pure hydrogen. And this have an impact, let's say, and this shows the importance of consider hydrogen carriers like ammonia, like methanol, as well, or a product as it is, a product itself that can be transported and exported as a green product, or let's say we can even think to transport pure hydrogen via this media. Obviously, if we consider not to use, let's say, ammonia or methanol as a pure material, but we would like to extract hydrogen from them, we have to consider that we had to add some capex, some investment, for what concerns the desorption of hydrogen in the arrival place, so Europe. Okay, so these costs, for example, of transport should be a little bit modified, because we have to include the capex related to what? The capex related to the synthesis of hydrogen. One aspect that is relevant is that obviously bringing hydrogen for combustion processes is meaningful, because at the end we can save carbon tax if I transport hydrogen, low-cost hydrogen from Africa to Europe, and I use this green hydrogen in Europe. Of course, I can save carbon tax in Europe that alternatively I'm not, in Africa I'm not paying, or I'm paying at lower cost. But nevertheless, the cost of carbon tax in this moment, or even considering up to 200 euro per ton of CO2, that is, let's say, 3 times more the current European average value, the cost of carbon tax do not compensate the high cost of green hydrogen. And therefore, even for what concerns combustion processes, it could be better, let's say, to consider to produce them close to the production site, production site of hydrogen, and somehow decarbonize the full production. So I hope you had the chance to follow me well. The goal of my presentation was, as I said, mostly to show that having the possibility to locally use hydrogen, considering the complexity of mobilizing hydrogen, is much better, let's say, but also because we can not only think to use hydrogen to produce carriers and then these carriers to be moved from Africa to Europe, but also to produce pure products that already are produced in in Africa, sometimes even by European companies, and then move these products, exploiting the already existing transport and logistic value chain to Europe. One last comment is this, that it could be interesting maybe also to encourage European companies that have steel manufacturing plants, concrete manufacturing plants in Africa, to have the chance, thanks to the using of green hydrogen at local level. This could be a good, there could be the possibility to encourage this company to make investment in directly in Africa, let's say, maybe via a sort of carbon credit compensation. So I mean, for example, thanks to the fact that I'm not emitting any more CO2 in, for example, Morocco, South Africa, or Kenya for a ton of steel that I'm producing thereby, the CO2 credit that I'm saving in these countries can be used to pay somehow the carbon taxes in my European manufacturing plant. Okay, so this could be this possibility to compensate via carbon credit wherever we are emitting CO2 or we are not emitting CO2 could be actually a very wise instrument to encourage, for example, European manufacturers to produce products, produce green products based on green hydrogen in Africa. I hope everything is clear. Nevertheless, I'm there for any question.
Thank you for your presentation, Stefano. It was super interesting and super clear with your colorful slides. I would like to ask if there is any questions in the participants. Yes, please, Milou.
Hello, everyone, and thanks a lot for the presentation. I have two questions. First one, you have this analysis based on 3 countries.
Yes.
I was wondering how you came to this selection. Also, since we see that Egypt is presenting itself as a potential hub for green hydrogen, but I didn't see Egypt in your analysis. So that was my first question. Second question. Do you also happen to have some insights in the cost of producing these products with green hydrogen in Europe? Because some of the thinking may be that renewable energy costs are lower in Africa, so green hydrogen would be cheaper in Africa compared to Europe. I was interested to see if there's also any way of saying producing these products in Africa with green hydrogen may be more cost competitive than producing it with green hydrogen in Europe.
Okay, so thank you for your question. First of all, to answer to the first one, the reason is that our partners from Africa in Just Green Africa are coming from these countries. So we had the chance to have access to more precise data related to local renewable production, etc., and therefore have a more precise cost estimation for the levelized cost of hydrogen. So the reason is quite straightforward in this case. Regarding the second one, the second question, well, the point is quite, the answer again could be simple, I think. Well, first of all, let's say, it's obvious that generating according to my slides here, for example, it's quite straightforward to say that if we would like to produce for example, steel or ammonia or gasoline in Europe with hydrogen produced in Africa, and we are transferring hydrogen as pure hydrogen, you have to consider that more or less you have to sum up these two values, for example, or these two values. So meaning that at the end of the day, for example, the cost of hydrogen coming from Morocco to Europe is at least at least 6.7 euro per kilogram, at least, and therefore then I have to use my my hydrogen to, let's say, evaluate how much hydrogen is needed per each let's say kilogram of ton of material. Okay, so I have mostly to sum up this cost and use this cost let's say in the previous evaluation of cost. If we obviously look at cost of production of green hydrogen in Europe, because obviously the same exercise that we are doing here can be done with the cost of production in Europe. Well, there are areas of Europe, particularly I would like to mention, for example, southern Spain or areas with very high wind potential, where it can be possible to get levelized cost of hydrogen close to 5 to 6 euro per kilogram. And obviously, let's say, if we use such value, more or less we land to the same values of production, okay? But if we consider other areas where you have lower irradiation or lower wind potential, at the end, the green hydrogen production cost can be 8, 9 euro per kilogram, even more. And at the end, if you think that the overall cost of green hydrogen on the product becomes 60, 70, 80%, the more the cost of the more the cost of hydrogen is, and the more the more my final product will cost. Obviously, we did not do this analysis, I would like to say, but let's say in principle, I think it's easy to get the values. Let's say.
Thank you.
So what is for sure not meaningful is to bring, let's say, pure hydrogen, and particularly for some pure hydrogen from Africa, and, for example, synthesize methanol or gasoline in Europe. Better to do this type of synthesis directly in Europe, in Africa, and then transfer it.
Thank you very much. I have a simple question, or maybe not simple, but just to know, do you know if it would be the same for the countries that are bordering the Mediterranean, but on the Mashrek side, so on the close Eastern Middle East?
Let's say for aspects related to solar irradiation, let me say, if we compare with, for example, Morocco and places where we considered only PV as a renewable source, I think that the values could be similar, so maybe landing around 6 euro per kilogram. Regarding the, let's say, Middle East area, I know, for example, the wind potential is a little bit lower than the oceanic areas of Morocco, for example. So in that case, you cannot exploit both the contribution from renewable. You have to consider that the best levelized cost of hydrogen value comes when you have an area that can guarantee, for example, 2,000 equivalent operating hours per year of PV, and at least 2,500, 3,000 equivalent operating hour for wind, because PV is much more less capex intensive than wind, of course, but the number of hours that is able to operate are lower. So for wind, I need really to have at least 3,000 hours, so 1,000 hours more than PV to be comparable and competitive in the production of low-cost renewable energy, and therefore low-cost hydrogen, because we always have to remember that in the levelized cost of hydrogen, the cost of electricity has an impact around for at least 45, but even 60% of the overall cost of the production of green hydrogen.
Makes sense. Interesting. Thanks a lot, Stefano. Do we have any other questions related to Stefano's presentation? Yes, please, Hadi.
Thank you, Tiziana. Thank you, Stefano, for the presentation. I hope you're hearing me well. Just a question, I'm not sure if you mentioned this in your slides, related to the transportation using pipelines. So did you take into consideration using existing pipelines, or
yes, in
the cost of repurposing these pipelines, or installing new pipelines?
Consider that in the study, for Morocco case studies, once we did the comparison, we considered both possibility to transport it via liquefaction as well as to transport it via pipelines. So
new pipelines, you mean?
No, existing pipelines. So using the possibility to integrate 1% of in mass of hydrogen in the natural gas stream.
1%.
1%, yes, only
Okay.
in mass, 1% in mass.
Thank you.
And therefore, for the cost, we considered the cost of flowing, mostly, I don't know how to say it in English, the charges for transferring a certain amount of material through the pipeline.
Yes, please. Thank you.
Thank you. We have also a question in the chats. According to the H2 Atlas, West Africa has significant potential for green hydrogen. Are you open to partnerships in West Africa? And this is a question from Saliha Keita.
Yes, we actually we are working with GIZ, with Jülich, that is involved in a project also funded by GIZ, Germany, for what is concerned the exploitation of West African areas. West Africa, in particularly the area of Ghana, is the fourth, let's say, use case of Just Green Africa. But as we do not have a local partner, we did not have the access to very precise data on specific hotspot as we could have for the other countries. But I can tell you that, for example, we just submitted in the end of October a deliverable related to production cost estimation of green hydrogen in Africa, and also the West Africa, in particular the Ghana area, has been evaluated. So more than happy to further work on this topic in West Africa countries as well.
Good to know. Do we have any other questions? If not, then we can move on to the next presentation that will be given by Antonio Tuzio. He will examine the potential for technology transfer across sectors in African countries, supporting innovation and driving the growth of the green hydrogen markets. Please, Antonio, if you can take the floor.
Yeah, thank you. So just a second, I share with you the presentation. Okay, can you see it? Is the right?
Yes.
Right. Okay,
right format.
Perfect. So sorry if there is a lot of confusion in the office today. I hope you don't hear it. So hello everyone, I am Antonio Tuzio from STAM, and I'm responsible for the development of the technology and manufacturing value chain roadmap. Here you can see the table of contents of the presentation that I will follow today, and I want to give you a brief introduction before starting to tell more about the work in the Just Green Africa project. So a brief introduction. As you may already know, there are different kind of technology to manufacture green hydrogen. We have the alkaline technology, the PEM, so the polymer electrolyte membrane, the solid oxide technology, and the anion exchange membrane. However, in the context of Just Green Africa, we are not considering all of this technology, and the reason is explained in the next slide. As you can see, these are the current state of the art about the production and manufacturing of electrolyzer, and which are the future forecast. And you can note that the share that will be covered by the anion exchange membrane technology and of the solid oxide technology will be very little if compared to the PEM and the alkaline. So that's essentially the main reason why we will consider in our study only these two electrolyzer technology. If we want to go into detail about the structure of an electrolyzer, I would say that we can divide it into two macro groups, the stack and the balance of plant, the so-called BOP. The stack is the real core of the technology, and for this reason is strictly its, let's say, structure is strictly dependent on the technology. On the other side, we have the balance of plant, where the main components are more or less similar regardless the technology. Here you can see an overview of the stack composition, both for the alkaline and the PEM technology. There are a lot of differences. The first that you may note is that in the alkaline technology we have the electrodes and the diaphragms that are, let's say, surrounded by a liquid electrolyte solution. This is not true for the PEM technology. Other key differences regard the raw materials employed in the structure of the electrolyzer. You may already know that precious material are involved in the PEM technology, and this is not happen for the alkaline one. And this is one of the main reasons for which PEM technology usually costs more than the alkaline one. So this is the brief introduction to the main themes of the following slides. Here, as I said to you before, the structure of the two typical balance of plant for the alkaline and for the PEM. The configuration of these elements are different, but more or less we can say that they are very similar, because we have a water demineralization unit, pumping devices, electrical devices, heat exchangers, tank, and so on. So even if the configuration is different, the elements, the components of this BOP are very similar. So the first aspects that we are assessing in our work is the possibility to build new manufacturing facilities. Obviously, when we need to do that, we need to account for several factors, several parameters. And the first one is which are the raw materials that we need if we want to manufacture an electrolyzer. As I said before, the two technologies are different, so we need to consider both when we want to do some calculation about raw materials. And here you can see reported in these two tables which are the raw materials employed in a structure of an electrolyzer, and 1 megawatt is used as a reference. You can see that some of these raw materials are common to the two technology. For example, if we look at steel, aluminum, and copper, while other raw materials are more typical to the technology itself. For example, we have zirconium for the alkaline, but this is not true for the PEM, where we have titanium, platinum, and iridium. Obviously, if our aim is to define a roadmap, we need to consider that this is a sort of snapshot of this type. But when we have to look at the future, we need to consider that these compositions will change. So this is essentially because it's not, as I reported in this slide, it's not a mystery that the current efforts made by researchers and scientists is to find day by day new ways to reduce the use of critical raw materials, as well as to find components and materials that can be easily recyclable, for example, at the end of life. Here you can see other information about which is the manufacturing energy divided both for the stack and the BOP of the two technologies, and how cost is divided according to the components of an electrolyzer. As you can see, since let's say that the stack is the more technology advanced part of an electrolyzer, it covers the major share, both for the alkaline and for the PEM, a little bit more for the PEM. And then we have minor share for the power electronics, the gas conditioning, and the balance of plant. As I said before, due to the engagement of more precious material, generally the average cost of a PEM electrolyzer is higher than the alkaline one. So once did this premise, there are a lot of answers that we need to, a lot of questions that we need to answer. Sorry. The first one is do we have enough raw materials in Africa to manufacture electrolyzer? And likely the answer is yes, because there is at least one African country that has a large mine production and large reserves to allow the manufacturing of electrolyzer. Here I've reported some informative tables about quantitative measure about PGM production and reserves, rare earth materials, natural graphite and copper. Here you can see data about alumina, iron ore, nickel, but also zirconium. So a lot of numbers that in some ways tells to us that we have enough raw materials to start at least this manufacturing value chain. But then let's say that the raw materials availability is not sufficient, because we need to assess also the other steps of a manufacturing value chain. And so the capability to process these raw materials, to manufacture the components, and then to assembly at the end of this manufacturing. But unfortunately, as you can see from this slide, even if Africa has enough raw materials to manufacture electrolyzer, there is a lack of expertise and knowledge in process manufacturing of components and assemblies. These things is not true if you look at China, for example, and it is let's say of a common knowledge that the largest share of raw materials are currently exported to China, where value is added, where these raw materials are processed, and then maybe the same raw materials that left the continent come back to the continent, come back to Africa as a final products. So this is for sure a weakness in this sense that obviously has to be considered. So as I said before, there is a lack of expertise and knowledge, but one of possible questions can be which are these knowledge, which are the figure that we need if we want to establish, if we want to develop a manufacturing value chain. Well, here I divided this figure according to one side the career level, and on the other side according to, let's say, the field of expertise. And you can see that for sure we need a lot of knowledge and experience, from let's say in brackets common plant operator to chemical research engineer, manager, editor, and so on. I have also found some information about also which are the main occupation that we need if we want to physically build a new electrolytic hydrogen facility. And so we go from metal workers to, again, engineers, production occupation, while for the ongoing operational and maintenance job, as we said before, installers, maintenance, repairers, engineers, plant system operators, and so on. So obviously, in the definition of a roadmap, this is one of the way that we have, but it is not the only one. We have other possibilities, and one of these is the so-called technology transfer. So the aim of this chapter is essentially to analyze which are the current technologies that in some ways share similarities with electrolyzer, and so we want to understand if there is the potential to transfer this capability to manufacture this technology to the manufacturing of electrolyzer. And the first idea that comes to mind is, when we consider especially a PEM electrolyzer, is the PEM fuel cells. This because regarding both the physics of the fuel cell, but also from the chemical principle, the electrochemical principle at the base of this technology, there are huge similarities. But unfortunately, as for the case of electrolyzer, there is no diffuse production in Africa of fuel cells. One exception can be, let's say, South Africa, where we can find some small manufacturer of fuel cells, but this is, let's say, a more reasoning that is detailed for that country. Here we are looking at the continent in general. Then another possibility that we have is the batteries. Batteries, similarly to fuel cell, share a lot of similarities, both for their structure, because if we look at the structure of a lithium-ion battery, we have two compartments, we have electrolytes, we have a membrane in the middle for the ion diffusion, and obviously is an electrochemical device. So at least in theory, there is enough potential to transfer the manufacturing of this technology, and so to shift from batteries to electrolyzer. But as for the case of fuel cell, there is no diffuse production of batteries in Africa, also because for the battery, there is the same problem of processing the critical raw materials needed for the manufacturing. Next in line is the chlor-alkali industry. Here, I would say that the reasoning is different, because for the chlor-alkali industry, so for the chlorine production, the main item used is an electrolyzer. Obviously, the final goal is different, but here we are using an electrolyzer, but let's say in a different way with respect to technology that we have seen before. In Africa, we have enough production of chlorine. And here I've reported, just to let you understand, which is the production of chlorine in Africa, in some African countries, also compared to European countries. And you can find that this production is comparable. So we can say that maybe chlor-alkali industry is one of potential industry that can be able to do this technology transfer for real. Then the membranes and chemicals, as I showed to you the structure of an electrolyzer, membranes and obviously chemicals. If we think about the electrolyte implied into an alkaline electrolyzer, is for sure of huge importance. However, we need to face another issue for African countries, and this issue is that it can happen that we are not able to find data about the production of some industry, and this is exactly the case of membranes and chemicals, but we are working on this theme. Next in line is the power conversion technologies, and here there is, I would say, a strong link, in particular with the green mobility. On a first aspect, I would say that why power conversion systems are important, because electrolyzers are fed by a direct current, that should respect, let's say, important range, important parameters. It is not said that the current in output from the renewable sources is in line with the parameters required by the electrolyzer. And so in some ways we need to adjust this input, and we do that thanks to power conversion system, as you can see in this slide. Regarding the synergy with the green mobility, you should think about this fact that when we talk about green mobility, we're talking about vehicles that are powered from a battery or from fuel cell. So if electrical devices have been developed to operate with this device, maybe the effort that should be made to operate with electrolyzer is not so huge, let's say. That's why we are considering also this sector. Then last one, there are the mechanical components, and here it is, I would say, a macro groups, because here we can talk about pumps, we can talk about valves, tanks, and so on. These are more, let's say, components involved in the balance of a plant rather than a stack of an electrolyzer. And here you can see the adjustment that currently are studied in order to, let's say, let these components to operate with hydrogen. You maybe already know that one of the major problems of mechanical components when operating with hydrogen is the one of embrittlement, or anyway the fact that hydrogen molecules are very, very little compared to, for example, natural gas or the common fossil fuels that we already know. We need to adjust these components in order to operate in safety, obviously. The other aspects that we are studying, we are assessing in our project is the not technology but know-how or capabilities transfer. Here there is a slight difference with respect to technology transfer, because here we are not assessing technologies that are similar to hydrogen, but here we're assessing industrial sectors that currently operates with hydrogen, and maybe there is the potential to transfer this knowledge for the benefit of the manufacturing of electrolyzer. And the first sector that we analyzed is refineries, even if can appear, let's say, in some ways contradictory, because refineries operates with fossil fuels and we're interested in green hydrogen. This is not true. Firstly, because we have a lot of operational refineries in Africa, and you can see in this map how they are distributed geographically, but you can see also which is in numbers the production of all oil refinery, also divided by the major countries and compared to other regions of the world. But you can see also in this refinery scheme how many processes involve hydrogen in a refinery, and maybe and mainly they are hydrotreatment and hydrocracking process. So maybe you agree with me that there is here expertise, there is knowledge that can be shared for the benefit of electrolyzer manufacturing. Another sector that we analyzed is the production, the manufacturing of fertilizer. I have reported to you which are the main which are the main region in the manufacturing of in the manufacturing of fertilizer. Africa is not the last country, but nor the top, is in the middle. And how throughout time the manufacturing of this fertilizer has changed. And you can know that nowadays half of the manufacturing of fertilizer is nitrogen based. This means that this industry is operating with ammonia, and ammonia is a molecule based on hydrogen. This means that there is field to transfer the knowledge accumulated by the fertilizer industry to the manufacturing of electrolyzer. Last one, and as already mentioned by Stefano in his presentation, is the direct reduced iron. I would say that the only difference of this industry with respect to refineries and the fertilizer production is, I would say, the TRL, because direct reduced iron is a more innovative concept, let's say. But this is not negligible, because if you can see, I don't know if you can see numbers from, maybe the picture is too small, but year by year, the manufacturing of direct reduced iron in Africa is growing. So I would say that it is not so negligible, and Africa can be one of the leading country of one of the leading region in the world that can exploit for sure this new product. As a last aspect, we are also trying to identify which are the major industrial associations that are operating for the growing of green hydrogen. I would say in general, not only regarding the manufacturing of electrolyzer, because when we talk about industries or university, we are covering the most complete value chain, so from the production to the delivery of the final products. So these are as of so far the main industrial associations, but also I've tried to put examples of university courses that have established green hydrogen let's say path in order to let's say form to build the future generation, because obviously when we are talking about roadmap, we need to look at the short term, surely, but we have let's say we have to look also at the midterm, and so if we want to put some indication 2040 and the long term 2050. So we need to build a new generation in order to grow the knowledge, the expertise in the continent, and in order to, let's say, not let foreign countries to do the work that Africa can do alone. So here my presentation, and I hope to be in time. And if you have any question, please feel free to ask.
Perfect timing, Antonio. Thanks a lot. Is there any questions from the participants? Milou, please.
Yeah, thanks again for the presentation. Very interesting. Just a general question. You are referring several times to the roadmap. Is the roadmap still under development, or is that also something that is ready and that we can have a look at?
No, it is not ready simply because to develop a roadmap, we need to have the complete database on which the roadmap will be based. So once we will have the full information about also, as I said before, if you consider, for example, the production of membranes or electrolytes, we are not data so far. So when we will have all the possible data, we will have the enough tools, let's say, to set also objectives in the short, medium, and long term. So the roadmap is the final objective, the final aim. This is the material needed to prepare the roadmap.
And do you have a timeline for that roadmap and when you might expect it to be ready?
So yeah, the project finished at the end of January. So we have 1 month now to let's say put together all of this information and to prepare it.
Okay, great. Looking forward to see the results.
You're welcome.
Thank you. Haya.
Yes. Thank you, Antonio. In your presentation, you spoke about hydrogen and fuel cell related jobs and also the job needed. As the MedGem network, we are trying to work on identifying gaps and fill some on-demand capacity buildings curricula. So, in your eyes, which are the most emergent sectors of activities or related jobs? Is it in top, middle, or technical management, or are these countries have to face and to offer a capacity building for all these sectors at the same time? And did you manage to come across studies that have recommendation on where to start and how to build this capacity, and how European Union can help doing this for these countries?
Yeah, I would say let me come back to the slide of careers, let's say. So here we are. So I have a partial answer to your question. So I would say that every of this figure is important into the development, because as in a value chain, I showed to you the value chain before. We have the extraction of raw materials, but then we have processing, we have the assemblies, and so on. You can see that even if we have a large pool of engineers, but we do not have expertise in how to manage a plant, everything will fall down. So if we need to identify priorities in this sense, I would say that each of these figures should be present, should be, let's say, formed. There is not, or I would not say that there is one most important of another's, independently of the career level.
If I may add on this, Antonio, we've made a full inventory of all the green hydrogen courses that are established in the MENA region. So maybe that would be helpful for you also to receive, because, for example, in Morocco, there is many more than the one mentioned. So that just to share, just waiting a few seconds more. If not, this will be the end of the webinar. On behalf of MedGem, we apologize for not giving the last presentation, but for personal reasons, Frank Waters was not able to join this meeting, but we will make sure to share the slides and PowerPoint so that you have at least the content and all the notes. We can do the same with Antonio's, maybe. Are you okay that we share your slides, Antonio? All good. Then all slides will be shared, and then in the comments we have, so South Africa is in partnership with GIZ. They have the full skills for the hydrogen economy, including the renewable and electrolyzers. Yeah, GIZ skill roadmap. Yeah. Indeed, so we have that as well.
Thank you, Dandeka.
Thanks for sharing. All right, then. If no further comments, I wish you a bon appétit, as we say in French. Enjoy your lunch and the rest of your day. And thank you for joining.
Thank you.
Bye-bye.
Thank you.
Bye-bye. Have a good day.
Thank you. Have a nice day, everybody.
Bye-bye.